Okay, welcome back, welcome back. Happy Monday. So we begin on page 9. If you could open the packet to page 9, that would be super. So today is the first day that we have folders on the tables. So for most of you, it'll look familiar. If not, just ask somebody what to do. You're going to put your name there and you're going to sign in every day with the time that you arrive. You're also going to come in every day and put homework in there and put questions of the day in there. And when we take quizzes, they'll go in there. Projects will go in there. Everything you're going to turn into me is going to go in there. And then when I put the folders back on your table next class, you'll take out all the stuff that is graded. Okay? If there are any questions on that, again, just ask somebody sitting next to you. Somebody at your table definitely knows what to do with that folder. We'll take our quick look at the calendar. Today is our second class. We're going to review the definite integral today, and then on Wednesday we start what we'll call the new stuff here in chapter 6. Our first quiz is February the 4th. What day is that? Is that next Monday? A week from today? Yep. Okay, so a week from today is our very first quiz. This coming Friday, our very first project is due. Right, so hopefully we started looking at that. You have all the tools. The first project is essentially a review of Calculus 1 stuff, so nothing really new there, but go ahead and take a look through that if you hadn't had a chance yet. Any questions on the calendar? Okay, and then a resource that you will have available to you, same as I did last semester, I record the classes. You can see I've got the Bluetooth in my ears, so if you are interested in checking out a video, you will see everything that happens up on the smartboard and you'll hear everything that I say. Unfortunately, you won't hear questions or feedback or anything from you guys because you're not mic'd, but on the syllabus, it tells you how to get there. So if you want to see all of my videos, you can go to this link. If you wanted to see the video from a particular date in time, you're typing in something like that. 202, that's this course, 2013, that's the year, and then you find a particular date. So March 3rd, you type in March 03. It's always a 2-digit day, okay? So if you went back and looked at the date for last class, it was January 25th. I bet you could find the video from Friday's class. All right, so check it out if you haven't done so, if you haven't seen any of my videos before. Not that you need to rewatch that first class necessarily, but just to make sure that you can access them, all right? Okay, so again, we're here on page 9, and we'll start with number 1. Can we go to Richard? Thank you. Give it a shot. Okay, so we ended up starting with a graph. I'm actually hoping that the graph of y equals sine of 2x is something you can figure out. It's the same as sine of x, but you'll have 2 of them, right? It's compressed horizontally. Okay, and so here's the graph on the calculator. We can go 0 to 2 pi, and then we know that it's not going to get any higher than 1 or -1. So it's easy enough to set the window, and then you'll get a graph, and then we can ask for the integral. One thing a few of us made a mistake on was being in degree mode. We will never be in degree mode in this classroom. So every time you walk through this door, you put your calculator into radian mode. So here's one problem that some folks had. If we go up to second calc and then number 7, which is the way to find the integral, it says lower limit is 0, upper limit is 2 pi. Now, we get this error, and the reason the error is happening, it's just poor programming, to be honest. You have to make sure that the maximum and minimum are inside of your window range, so between 0 and 2 pi, and they are, so it seems like it shouldn't be a problem, but changing this to a number slightly bigger, which moves the window a little bit further to the right, should fix the problem. I don't know why it's a problem, shouldn't be a problem, but this will work now if we just try the actual integral. So we'll try again, number 7, 0 to 2 pi. Okay, so now we don't get an error. So if you ever get that kind of error when you're trying to integrate, just make your window different. You got to make sure the thing you're interested in integrating is all there. Okay, what is this number very close to? That is very close to 0. That e -14 means times 10 to the -14. So I'm getting 0. Does it make sense? Yeah, absolutely. If stuff above is positive and stuff below is negative, then everything there is going to cancel. So if I really wanted to find the actual area, what I'd need to do is maybe only go from where? from 0 to pi over 2, and then 4 of them, right? So that might be the best way to go. So if you integrate 0 to pi over 2, you get a nice number. How much is the area of one hump? Is 1. So the area of all the humps is 4, okay? And yeah, I really like what this table did over here. If you don't want to bother with trying to deal with where does it become positive and where is it negative, you can insert the absolute value, which is inside of the math menu. And it's 1 to the right there under number, and it's the very first option, ABS. So this is going to tell me what the graph of the absolute value of sine of 2x looks like. All the positive humps, where will they be? Still positive, they won't move, but all the negative humps, what's going to happen to them when you take absolute value? They're going to become positive. And so we'll get the same kind of picture, but it'll kind of be like a bouncing ball here. Maggie?
How did you
Yeah, so if I just type right now, the calculator's automatically in type over mode. But if you wanted to insert, it's up here, that yellow INS. So hit that, and then you can type. The cursor changes a tiny bit, I think. Right now it's a solid rectangle, and it changes to like an empty kind of, or just a horizontal line, I think. You're welcome. So we've got that picture, and then we can actually ask it to do the integral all the way across 0 to 2 pi, and we should get the 4 that we were expecting. Mm. So I'm not sure. So the 2 was inside of the sine function before.
Oh.
Yeah.
Sorry, went wrong.
Okay, so we get the area of 4. Any questions there? Okay. Next page. Number 2, we're back to tacit A. Okay, so see if you guys can remember what it means to draw left-hand rectangles. Left-hand rectangles. So this is a multiple choice. In the first one, you're drawing rectangles on the interval -3 to 1. So draw some rectangles between -3 and 1. Decide whether you think the left sum approximation is an under or overestimate of the true area. One of those choices is the right one. All right, so we had all of our tables, I think, honing in on part C, or choice C as the right answer. Remember, left rectangles of the 2 points you're trying to choose between. Of the 2 points you're trying to choose between, you pick the one on the left-hand side to determine the height of the rectangle. So between 0 and 1, which one do we pick? For left rectangles, you pick 0. The one on the left, go up to the curve, that determines the height. Go over, come down, that's your rectangle, okay? And because that part of the curve is decreasing, all of those left rectangles are above. All right, good. Let's move on to number 3. So number 3 is going to be our definite integral refresher. And with apologies, the rest of this page is just going to be me yapping. But we'll try to get through it quick. The goal here is to try to understand the really crazy looking symbols at the bottom of this page. This is the goal right down here, is that. Now, it's something that if you took this class to Calc 1 with me last semester, you saw this exact thing not once but twice. And I'm guessing that very few people got it the first time, and maybe we grabbed a few more people the second time. So if this is your third time, perhaps we'll grab you this time. It's just quite messy in terms of notation, but I think the ideas are not hard. So stick with it. Let's see if we can try to understand those symbols at the bottom. So here's the idea. We are trying to estimate area under a curve. We've been talking about this. We talked a little bit about this today. So to estimate area under a curve, what we're going to do is take our function. It's going to go between some x value called a, and it'll end at some x value called b. For right now, let's assume the function is positive the whole time, and then we saw some negative, like the sine function was negative before. And what we're going to do is we're going to chop this interval right here up into a bunch of different pieces. We're going to pick n different pieces. We're going to cut here so that we have n different intervals right in there, okay? And so those different points on the x-axis, or the t-axis, they're going to get names. And so you can see the names. The first point is t0, next one is t1, then t2, all the way down until tn is the last point down there, okay? So you cut the x-axis or the t-axis into n different pieces, n different intervals. So let's first see if we can fill in this blank here. We want to know the width of each interval. Well, how long is the whole interval? How long is that? It has to do with A and it has to do with B. With B minus A. Yes? Okay. And how many pieces are we cutting the thing into? N pieces. And we're assuming they're all equal in length. So how much is each piece? How long is each piece? B minus A over N. Okay? Whole thing is B minus A. Cut it into N equal pieces. And delta T is the symbol we use because it's supposed to represent a little change in T, a little width. Okay, so then how do we estimate this true area under the curve? Well, we could use left-hand rectangles. So between the first 2 points, which are T0 and T1, right now we're just doing left-hand stuff. Which point do we pick, T0 or T1? You pick T0. You go up to the curve at T0. That determines the height of this first rectangle. You go to the right until you're right above the next point. You go straight down. Is that rectangle an over or under estimate of the true area? It's under, because it was a left rectangle and the function was increasing. Then we move on to the next interval. Actually, let me pause right there for just 1 second. This distance right here is f of t0, right? It's the function value, it's the y value at t0. We agree? That's the height? Okay, let's move on to our next rectangle here. Between t1 and t2, still doing left-hand rectangles. Which point do we pick? Pick T1, the left-hand point. You take T1, you go up to the curve, you go over to the right until you're directly above the other point, straight down. What's the height of that rectangle? It's f of T1, right? Because we're picking T1. T2 is not important here. The height of this rectangle is f of T1. And you can keep going. What's the height of the next rectangle going to be? F of T2, right? We can kind of see the pattern. How about the very last rectangle? Between Tn minus 1 and Tn, left-hand sum, which point do we pick? We pick the Tn minus 1. So we go up to here, over, and down. And we actually never see the Tn. We never see that top point there. And so if I wanted to find the area of the red rectangle, for example, I'd say, okay, the area of a rectangle is height times width. The height is f of T0. The width is this little delta t. We called each of these widths delta t. They're b minus a over n, but delta t is the width. So the area of that very first rectangle is f of T0 times delta t. The very next rectangle, the one in blue, how much is the height? F of T1. How much is the width? Delta t. The area of that rectangle is f of T1 times delta t. And it proceeds merrily along, and you just add up the areas of all these rectangles. Notice the last one is actually the n minus 1 because it's a left rectangle. And you add those guys up, and that's what we're calling a left-hand sum. And for a right-hand sum, it's almost exactly the same, except for the very first rectangle, T0 or T1. Which one do we pick for right-hand sums? We pick T1, which means we never see which point. We never see the T0. So you'll notice the very first point there is T1, and T0 doesn't appear in that bottom row. And we make up for that at the end, the very last rectangle. Which one do we pick if we're doing right rectangles? We pick the Tn. And so we actually do get to see the last point. And so it doesn't just end at f of Tn minus 1, which is the one that's second to last, but it ends at Tn. So they're exactly the same. Just you lose one term in the beginning and gain it at the end. Okay, number 4 is any questions on that? It's not too bad, right? Pick a height, multiply by the width, keep doing it, add them all up. Those are our right and left-hand sums. And now we're going to abbreviate using sigma notation. So maybe this is familiar to some of you, maybe not to everybody. But let's take a look at the right-hand sum and see if we can abbreviate using sigma notation. So first, sigma notation is so named because we use the Greek letter sigma, capital sigma. It's supposed to remind us of S for sum. That would be the left one. We're going to do the right one right now. But yeah, exactly. So the idea is to try to figure out what the basic pattern is. I'm going to grab one of these guys right here. For example, this thing right here. delta t times f of t2. Looks exactly the same as the prior term, delta t f of t1. The only thing that changed was that little subscript, right? They're all exactly like delta t f of t. So that's what we write over here. Delta t f of t. And the is something we just have to replace with a letter. And that's right. So the letter we're going to use here, well, let's use the same letter we used below. Sometimes it's I, sometimes it's K. We used I down here, so let's use an I. So right here, we're going to put an I. And how much is I in the very first term? Is 1, and then I is 2, and then I is 3, and all the way up until I is n. And so you indicate that over here by saying I goes from 1 to n. And again, the sigma means sum. It means you plug in I equals 1, and then you plug in I equals 2, and you plug in I equals 3, and you go all the way until you plug in I equals n, and you add them all up. And that's exactly what we did for this right-hand sum. Questions on the sigma notation? Dave? It is. There are kind of sneaky ways to make it so if you wanted to skip every other one, you have to build it into this formula right here. But yes, technically this guy has to go up by 1 every time. Okay. For example, if you wanted to put a 2 right there, then that would give you only the even numbers. Okay. All right. This next picture is supposed to illustrate something. What's it supposed to illustrate? Let's see, somebody we haven't heard from yet today. There are a lot of people we haven't heard from yet today. We know whether or not you are one of them. What are we supposed to see in this sequence of pictures? Yeah, we've got better and better approximations to the true area, right? In the first picture, you see a lot of white space under the curve, see a lot of blue space above the curve, right? Some of these rectangles, all the rectangles, bleed above the curve. But what happens to those white spaces and extra spaces as you increase the number of rectangles? Well, they get smaller. And so the idea here is to not use 5 rectangles like in this first picture or about 10 rectangles in the second picture. Let's use maybe 20 or 30 rectangles, or better yet, what can we do to the number of rectangles? We'll send it to infinity, right? And that's going to be our definition of area under a curve, and that's it right there. So the crazy sigma thing looks exactly like it did right up above. We wrote it out there. And the only new thing is that we're sending n to infinity. And that's our definition for area under a curve. And so why do we harp on all these crazy messy symbols? Well, we're going to end up seeing a lot of applications of the integral this semester. And it's not going to be so clear that integral is the right tool, but we are going to end up with things that look like this. In a variety of contexts, we're going to come up with stuff that looks like that. And so it's now our job every time we see that to say, oh, this is really just an integral happening here. Right? We have to recognize that thing because we're going to see it over and over again in the coming months. Okay, so let's go to number 6, and we are back to Bubba. Okay, so without saying anything about antiderivatives, I know a lot of you know stuff about antiderivatives. All we are doing is using that symbol right there to mean the area under a curve. That's it. That crazy symbol right there just means area under the curve. No more, no less, all right? It's just a way of avoiding writing all this limit and sigma stuff. But that symbol, the integral symbol, means area under the curve with the limit and the sigmas, all right? So let's move on to number 7. And we're back to Josiah. Okay, can you guys try A through D with your neighbors? Yes, Tiffany. I will. Okay, so let's come back together. And we'll talk about a couple of these. So the very last thing that we said was that the integral symbol just means area. Okay, turns out that I lied to you when I said that. The integral thing means signed area, because when you're doing this whole right-hand sum, left-hand sum, if all you're doing is finding, for example, f of some t value, it could very well be a negative number, right? Now, when we say area, we mean height and width are both positive numbers, but the symbols right here don't distinguish that they're all going to be positive. So if the function happens to be negative, then the quote area that you get is also going to be negative, all right? And so when we come here and we look at, for example, part B says go ahead and go from A to B. So that's from here to here. And every single one of these rectangles, whether you're doing right or left hand, are going to involve negative areas because you're just doing f of all of those points down there. So do we buy that the integral, even though I said it's area, it's a signed area? The integral is negative 10. Is that okay? Yeah, Angus. Yeah, when we do it backwards, the signs flip. So if we look at part D says go from C to A. So here we go. So going from C to A, Angus points out this is backwards. Normally we go from a small number to a big number. Well, okay, that's what I'd like to do first, actually. Let's just pretend we're going the small number to the big number. Yeah, that's what we do. So is this 10 a positive or a negative, just looking at the picture? That's a negative. Is that 7? That 7's a positive. So altogether, it's a negative 3 when we combine those two things, but it's backwards. And one of the properties of integrals says if you go backwards, change the sign. So we get positive 3. I'll write this out a little bit more. This is really the integral from A to C with a negative sign in the front. So it's the opposite of negative 3. Okay, move on to Sam, part 8. Okay, so maybe in a Calc 1 class you saw this towards the very end of the semester, but it's really important. In fact, it's one of 2 parts of something called the fundamental theorem of calculus. So if you have a rate of change in this picture is right here, and you wanted to find the definite integral of that rate of change, what you're actually going to end up with is the total change in the original function. Original function in my mind is f. Inside the integral is the rate of change, that's the f prime. What am I finding on the outside? I'm finding the total change of the original function f. So, so let's jump ahead to number 10. We'll come back and do 9 if there's time, but let's skip to 10. And we're going to Todd. Okay, so let's pause right there and just look at the picture, and then you guys will work through this in your groups. But let's just look at car 2, for example. So car 2 is the one that starts lower. And again, these are velocities that we're looking at. So do we buy that this velocity is really the derivative of some very natural function? What is velocity the derivative of? Is it distance or is it acceleration? Velocity is the derivative of the distance or the position function. So oftentimes, for some reason, physicists use S. I don't know why we can't use D, but I'll make Ted happy and use S for position. And so if I were to actually find the area in here, remember the fundamental theorem we just read, it said, well, you might already know. I mean, maybe you've seen this in physics enough. What does the area under a velocity curve represent? It's distance traveled, right? So maybe that's just something you've been doing for a long time in physics. So how does that play into the fundamental theorem that Sam just read to us? Well, in English, The definite integral of a rate of change is the total change. So the function in question here is a position function. We're looking at the rate of change of position. If you find the area under there, you're going to find the total change in position. The integral of this rate of change is the total change in position. So see if you can answer this question. Again, it's a multiple choice, and work with your neighbors. Okay, so I think some groups ended up looking at the area between the curves. I think that's oftentimes easier to think about. But if you look at the area between the curves for here, that represents the extra distance that car 1 has over the distance car 2 has. That's how far ahead car 1 is at that moment in time. You buy that? It's the difference between the distances they've traveled. So the question is, how far do we have to go to the right until that purple area is equal to the area up to some point? So is it there? Should I go a little more? Maybe another line or two. Maybe there-ish is where the two areas equal each other. And then from that point onward, car number 2 is ahead. Make sense? So I made a GeoGebra thing here. If you don't know about GeoGebra, you should check it out. You can just go to geogebra.org and download it for free. So I made a graph which estimates the paths of the two cars, or the velocities of the two cars. Does that look about what your picture looks like? Okay. And then we're going to start thinking about the areas between the curves. So as I sweep this guy to the right, areas between the curves, we end up with something like that. 0.56, the scale's not right because I didn't do the thousands or the feet per minute or anything, but 0.56 is the total area between the curves up to this point, which means that the one car is 0.56 feet, meters, whatever, ahead of the other car. Do we see it? And then what happens as we go to the right? Well, as we go to the right, the other car starts to be faster, and so it starts to gain back. It used to be a 0.5 something, now it's a 0.26 something. And what magic number are we looking for to answer this question? We're looking for a 0 when the one car overtakes the other car. And so it happens somewhere right around there, 1.55 on this. That's not necessarily the same as your graph because I just made up some points to estimate. Okay? All right, let's come back here and go to number 9. And we are now to Ashley. Number 9. Okay, so give that one a shot as well as part B.